Now we take a closer look at these special points for autonomous differential equations, which are called equilibrium points, and we look at their stability. So an equilibrium point y hat satisfies the equation f of y hat is 0. And now we can look again at stability. So it's locally asymptotically stable, or in short LAS, if for each initial condition close to the point, the solution converges to this point. And we call it unstable if solutions that starts close to y hat move away. So identify the equilibrium points and find their stability from the phase plot. So f of y, the function we are interested in, is y times 1 minus y, which is also y minus y square. So what do we have to do again? An equilibrium satisfies f of y hat is equal to 0. So this means y hat times 1 minus y hat is equal to 0. So we have two solutions. Y hat is 0 or y hat is equal to 1. Two equilibria. And they are right here and here, as we can see from the intersections. So which one is locally asymptotically stable and which one is unstable? Well, if we do our phase plot in this one, here we go positive, here we go negative, here we go negative. So then this one is clearly unstable because solutions move away. And then this one is locally asymptotically stable because solutions move towards it. That's cool, isn't it? Again, we just need to plot a function. As soon as we have that, we can do everything we want. So let's do that for the Allais effect function. So here we have the equilibrium point 0 and 0.2 and 1. And then these points are here, here, and here. And again, f is positive right here, it is negative here, it is positive here, and negative here, making this guy locally asymptotically stable, this guy unstable, this locally asymptotically stable. So what is what? 0 is LAS, this guy is unstable, and this is LAS. For this case, let us quickly also plot the solution as function of time. So like I did before for the logistic model, I draw a coordinate system with time here, and now the solution y of t here. So to get a similar picture like we had before, we first identify the equilibrium points, which are at 0, 0.2, and 1. But now they're on the y-axis, so 0 is here, 0.2 is maybe here, and 1 is here. Now being equilibrium point means f is equal to 0, so the solution doesn't change, it stays constant. So these are then the constant solutions as function of time. Okay? And now we take a solution maybe in between. Let's start here at 0.4 for the first case. So then 0.4 is here. This is the first case. And we know in the phase plot that the solution is increasing. It is increasing first a little bit, and then it would be increasing much more, and then would be increasing a little bit again. So it looks similar to what we see before. It gets steeper and asymptotes to 1. Another case, just for good measure. So let's say we start here, call this case 2. So we are beyond 1, so we are somewhere here. This is case 2. Then f is first of all quite negative, so we are steeply negative. We are approaching 1. Okay, and then what happens between 0 and 0.2? We haven't done this case yet, so let's look at that case. If we are somewhere here, let's call this case number 3. So then maybe somewhere here is case number 3. Then what? So at this location f is negative, but only slightly so. So we are decreasing until we go to 0. So this goes down to 0. Let me summarize. So we have seen before that the phase plot tells us where the solution of a differential equation is increasing or decreasing, or if f is equal to 0, we have an equilibrium. This means y of t is constant. We can also use the phase plot to understand stability of the equilibrium points by just looking at the little arrows. If the arrows point towards the equilibrium point, it is stable, and if they point away, it is unstable. Oh, excuse me, Tolo. What are you doing? Oh, you're finding your equilibrium. I hope you can find it. Oh.